Sangam Prabha. Digital India. Educated India.
Hello students, welcome again to the course Partial Differential Equation. So far in the previous lecture clips, you learned first order PD, linear, non-linear. You learned how to get complementary function and particular integral of a second order linear PD with constant coefficients. Also, mathematical modeling I discussed in the motivational introduction for wave equation, and in the previous clips you also learned some modeling for heat equation and Laplace equation. Now today I will consider the family of second order partial differential equation with variable coefficients, and I will discuss canonical classification and canonical reduction. Now, whenever you hear this terminology, canonical reduction, you must recall the 2D geometry, where you canonically reduce second order general polynomial equation in two variables x and y in one of the three standard conics called ellipse, parabola, and hyperbola. So likewise here, the family of partial differential equations, second order, with variable coefficients, what I am going to discuss today, will be classified in one of the three types called elliptic PD, hyperbolic PD, and parabolic PD. Okay, this is a very interesting topic. Let me first share this my whiteboard, digital whiteboard. Let me write here the family of second order PD, what I am considering today. The title is Canonical classification. Family of second order PD with variable coefficients, I will write in this form RR plus SS plus TT plus some arbitrary function of x, y, z, p, q equal to 0. Let me label it as equation 1. Symbols, for your convenience, I am again writing P is del z del x, Q is del z del y, okay, small r is del square z del x square, small s is del square z del x del y, and remember that del square z del x del y and del square z del y del x are same, and small t is del square z del y square. Before going to canonical classification, let me point out here something. One is one contains no non-linear second order terms. Okay, you see that if you introduce a second order linear operator R del square del x square plus s del square del x del y plus t del square del y square is a linear operator. And here I put xy in the argument of capital RST to remind you that RST are in general function of two independent variables x and y. Okay, let me now go to next page and start our actual discussion. First, I want to write down three canonical forms. Okay, so PD1 falls into one of the following three canonical forms. One is hyperbolic PD. This is the name, and its standard form is del square z del x del y equal to some function of variables and the first order derivatives. Next is parabolic PD. It is del square z del x square equal to some function of f, or maybe del square z del y square equal to f. Both are canonical forms of our parabolic PD. And last one is elliptic PD, which is del square z del x square plus del square z del y square equal to some f. Okay. Now, we will show that PD1 will be one of these forms based on values of a quantity s square minus 4RT. So it must recall you the quantity h square minus AB in 2D geometry, whose values are less 0, greater 0, and equal to 0. You are getting three conics, right? So here in next page, let me write down first nature of PD based on the quantity s square minus 4RT. So s square minus 4RT, if it is greater 0, it is hyperbolic. We will show this, we will prove this. First, I am stating the result. Equal to 0 means parabolic. Less 0 means elliptic. So now I will prove it. And in the process of this proof, you will learn how to reduce canonically in a general PD given in this one, in one of the three standard forms. That is called canonical reduction. So let me go to next page. So we need a transformation. What we will do, that we will change independent variable xy to xi and eta. Where eta and xi must be functionally independent. That is, it is well known that means xi x eta y minus eta x xi y not equal to c. Okay. So now we will have to compute P, Q, R, S, T by chain. So one by one, let me start. You see, first we rename, let me mention this. We rename Z, which was xy, function of xy, but x is now function of xi eta, right? So I rename it as zeta, which is function of xi eta. Okay. So we will use chain rule. That you know from the theory of several variables. Here, zeta is function of xi eta, right? Where xi is function of xy, eta is function of xy, so zeta is function of xy. So we can differentiate partially zeta with respect to x, and which is actually p, right? So p, which is actually, I'm using suffix to denote the partial differentiation. So instead of writing del zeta del x, I am writing zeta x. Remember, this zeta x is p because p is del z del x, and z and zeta are same. Just we are using different name for dependent variable because its form will change. We are not, we are transforming only xy to xi eta. We are not making dependent variable transformation. So zeta x and zx are same. So now if you use chain rule, you will have two terms from here. Xi x zeta xi plus eta x zeta eta. Should I explain this? I think it is clear because zeta is function of xi eta. So when you differentiate zeta with respect to xi, you have this term with a factor xi x. Similarly, when you differentiate zeta with respect to eta, you are getting zeta eta with a factor here. So Q will be similarly, Q is zeta y. It will be similarly xi y zeta xi plus eta y zeta eta. Okay. Now, smaller, it means zeta xx. So you have to differentiate the expressions of p with respect to x now, partially. Now you see that this zeta xi, like zeta, also function of xi. So to differentiate it, again two terms will come. And another term will come from here. So all total three terms will be there. Out of there, two terms are second order. So I am writing for second order. Okay, so you will have xi x square zeta xi plus twice xi x eta x. I will explain why factor 2 appears here. Xi x eta x zeta xi eta. Now, another term will be there, I will write later. But see, from this term, similar xi x eta x, xi zeta eta will come because xi zeta eta and xi eta xi are same as I told you. So this factor came too. Okay. So another second order terms will be plus eta x square zeta eta eta. To plus 2 first order terms, which is xi xx zeta x zeta xi del zeta del xi first order term plus eta xy zeta eta. So in next page, I need to go to next page to compute two more terms, s and t. So before going there, let me label this equation. So far I label it as 1 only. So we may label it as 2a, 2b, and 2c. So this may be 3. And this may be this may be 4, this constraint may be 5, and this computation may be 6a, 6b, so that 6c, 6d will be s and t, which I will compute on next page. So s, which is zeta xy, it is, I am now not explaining because by the time you understand, you have to use correctly the chain rule. Only you have to be very cool-headed so that no terms will miss. Okay. So xi x, xi y, zeta xi plus xi x eta y plus xi y eta x zeta xi eta plus eta x eta y zeta eta eta. Some more terms will be first order, so two terms will be first order. plus xi xy zeta xi plus eta xy zeta eta. What will be the equation number? It will be 6c. And last one is t, which is zeta yy. You can now do with me. It will be zeta y square zeta xi xi plus twice zeta y eta y zeta zeta plus eta y square eta y square zeta eta eta. Two more terms plus xi yy zeta xi plus eta xy zeta eta. It is 60. Okay. So now substitute all the terms PQ, RST in terms of new coordinates into starting PD1. So then you will have, of course, several terms, a number of terms there. So if to write down this equation, it will be 2-3 steps. So just I will write after by collecting, the coefficients of second order terms separately and then first order terms. So it will be, first I will write and then I will use I will introduce 3 functions to make it a compact form. So first coefficient will be of zeta xi xi will be r xi x square plus s xi x xi y plus t xi y square zeta xi xi. Next term will be 2, it is zeta xi eta. So it will be r xi x eta x plus t xi y eta y plus half capital S times xi x eta y plus xi y eta x. These full terms are coefficients of zeta xi eta plus we will have r eta x square plus s eta x eta y plus t eta y square times xi eta eta plus 2 first order terms will come from second order terms. Remember there is a given PD, there is a small f which is arbitrary, not given. So from there also there will be some first order terms will coming out for this transformation, but that we will not compute. We cannot compute now because f is arbitrary now. We can compute if some specific f is given. But for the second order terms which are given, 2 terms will come that we have to consider. So it will be r xi xx plus s xi xy plus t xi yy. So it will be zeta xi, similar terms plus r eta xx plus s eta xy plus t eta yy. So it will be zeta eta. Okay. Plus I am writing capital F as a small f will be changed. So some f. Okay, let me write down f below line so that I can write here there also the arguments. So okay, plus capital F. This will be of course function of variables xi, eta, zeta, and their partial derivatives zeta xi first order only zeta eta equal to 0. So let me label it as 7. Now, as I told you that I will now introduce in next page 3 functions, of which 2 functions you will get in usual textbooks. Third functions you will not get. This I am introducing so that it will be very easy to write down in compact form, and also formula can be remembered. Formula can be remembered for canonical reduction problems. So first is a function of 2 variables, which will be ru square plus suv plus tv square. Okay. What is the equation number I should give here? Okay. Let me give here 8a. B. It is 4 arguments is there. u1, u2, semicolon, v1, v2. Its definition is r u1 v1 plus t u2 v2, okay, plus half s u1 v2 plus u2 v1. Let me label it as b, 8b. And this is the third function I am introducing. It is a function of single variable u. Definition is r uxx, suffix denotes second order partial differentiation with respect to x, plus s uxy plus t uyy. Let me label it as 8c. So you see, the advantage of using this function is this. Using 8, transform PD, which I wrote in previous page, derive it, equation 7, reduces to, that means can be better is writing is rewritten as this form. A argument xi x xi y del square zeta del square zeta del xi square plus 2b argument xi x xi y semicolon eta x eta y del square zeta del xi del eta plus a eta x eta y del square zeta del eta square. You can write plus, in terms of my third function, you can write c xi zeta xi plus c eta zeta eta plus some function. Okay, I am using f bar which is function of, xi, eta, zeta, zeta, xi, zeta, eta equal to C. So now compare 9 with the forms I am writing here. Let's say this form. If you compare this, you will see that, okay, if both of these terms vanish, then it will reduce to hyperbolic. Now, when this function a will be reduced, will be 0. If you now look into the definition of a, you will see that this a can be written as a quadratic in u by v, if you divide by v, let's say. So that means you have to consider a quadratic, simple quadratic equation r lambda square plus s lambda plus v. Let me write down in next page. Consider following quadratic. R lambda square plus S lambda plus T equal to 0. Okay, so that means it has two roots, of course, lambda 1, lambda 2. Now, as from the theory of algebra, you know there are three cases. Case 1 is when discriminant is square minus 4RT greater C, which will give you two real and distinct real roots. Now, when discriminant will be 0, you will get only one root here, lambda. Real root, but only one root. Case 3, when s square minus 4RT less 0, you will get, of course, complex conjugate pairs, this, which belongs to complex group. So accordingly, you will have three classifications. Why? You see, go back to previous page again, and again see this argument of a is here not xi x, xi y. Here eta x, eta y. So corresponding to the roots of this quadratic, we can choose our transformations. Let me elaborately discuss case by case. So first case is, I am considering s square minus 4RT greater 0, which give us lambda equal to lambda 1 and lambda 2, which are real and distinct. I am putting xy in the argument to remind you that lambda 1 and lambda 2 are functions of x and y. Okay, so what you will do now, choose your transformation now in this way. Choose xi x by xi y equal to lambda 1 and eta x by eta y equal to lambda 2. What will be the equation number here? Let me see. 9 was there. So let me give this 10 so that it is 11. So 11 is first order linear PD, right? 11 is first order linear PD. So use Lagrange's method that you already learned. We discussed this in previous modules. So use Lagrange's method. So solving 11, you will get xi equal to some function of x and y. Let's say phi, and you will get eta equal to some function of x and y. Okay. Now, let me introduce two terminology here. Is 12 are called characteristic directions. Okay. Phi xy equal to C1. Remember, from Lagrange's auxiliary equation, you will get two arbitrary constants, which is this phi xy equal to C2. Okay. These are called characteristic curves. Okay. So remember, characteristic directions and characteristic curves correspond to roots of the quadratic tail. I'm showing you previously. So clearly, only hyperbolic PD has two characteristic directions. Because for two other cases you will see, for parabola it will be only one, and for ellipse there will be no characteristic directions. Okay, first let me finish hyperbolic PD case. So you see, because of this choice 11, both A is 0. So if both A is 0, what will happen? For the transformation chosen by 11, both A is 0, A xi x xi y 0, A eta x eta y is 0. So that means transform PD is now del square zeta del xi del eta is equal to some function of f, which is, function of independent variables, dependent variables, and first order derivative terms, zeta xi, zeta eta. So this is hyperbolic. This is standard form of hyperbolic PD. So you learn how to canonically reduce a general family of second order linear partial differential equation. Second order, it is better to say second order partial differential equation with variable coefficients and having linear second order terms. So here we conclude in this way. Hence, PD1 will be hyperbolic when s square minus 4RT greater C. Okay. Next, Let me consider case 2. Case 2 means s square minus 4rt equal to 0. So this gives us only one root, right? Real root, but only one root. So here what we will do, you will choose one transformation xi x by xi y equal to lambda, which will give you, as the previous, according to the previous logic, 1a vanishes. Of course. Now, remember, you have to, of course, choose eta, other transformation. So this, choose eta arbitrary. So that, remember, xi and eta must be functionally independent. So xi x eta y minus xi y eta x not equal to 0. Okay. Now, point is that you already know I stated that this case should be parabolic. But parabolic is, this is either del square zeta del xi square will remain, or del square zeta del eta square will remain. That means with 1a, b must also vanish. Now, actually b will vanish this case. Why? Because of an identity that I will not prove. I will give you as homework. At home, you can easily prove this identity. Okay. It is a argument xi x xi y into a argument eta x eta y minus b square argument xi x comma xi y semicolon, just for separation, eta x eta y. This is equal to 1 by 4 times 4rt minus s square into xi x eta y minus xi y eta x whole square. So let me label it as, let me go to previous page to see how much number we reach. 11. Okay. So let me give it as 12. So it can be easily proved if you substitute in the left side the definition of function a and b. Now point is that what 12 implies? 12 definitely implies b xi x xi y eta x eta y equal to 0 when s square minus 4rt equal to 0. Because why? You see, this term not equal to 0. Because xi eta are functionally independent. So it is not 0. And this term is 0 for this case. This term is 0. So that means b must vanish. So therefore, PD1 becomes del square zeta del eta square equal to sum f. I am not writing the argument of it, you know that. So this is parabolic. So you see, for this case, as you know, we prove now s square minus 4rt equal to 0 corresponds to parabolic PD. So now I will discuss the last case. It is the last topic in today's lecture. Now I will consider case 3, okay, which is s square minus 4rt less g, which means we will have complex conjugate roots, right? So still we can choose the transformation, although it is complex. These are roots of that quadratic. So if we choose, as in the case of hyperbolic, xi x by xi y equal to alpha plus I beta, okay? And eta x by eta y equal to alpha minus I beta. So of course, this will give you both a vanish, because this corresponds to roots. But remember here, note that we cannot say these are two characteristic directions, because characteristic directions means real thing. But these are complex, no? However, we have both a vanishes, and so that therefore transformed PD in complex coordinates, remember it is complex, no? Complex coordinates zeta will be apparently similar looking for hyperbolic. Del square zeta, okay, del xi, del eta equal to f. But this is not, of course, hyperbolic, because xi eta are not real here. So let me level this equation as, let's say, 13. So we need a second transformation here from xi eta to alpha beta, where alpha beta will be real. Now this transformation is very, very easy to guess. I think some of you already guess. So we need here second transformations to get back to real coordinates. Alpha beta, okay. So what we will do, we will make a transformation of xi eta to alpha beta, like 2 alpha equal to eta plus xi, naturally real part will come, and twice I beta equal to eta minus. So of course you are making a transformation, so you need to compute again the derivative term. But fortunately we don't need to compute all the derivative terms, because we have only one thing. This we have to compute. So what we will do here, remember that zeta is here because we have to find zeta xi. So zeta is a function of alpha beta, where alpha is half eta plus xi, right? And beta is minus I by 2 eta minus xi. So you see, if you now compute zeta using chain rule again, zeta xi, this will be zeta alpha, okay, and half del alpha del xi, right? Similarly, When you differentiate zeta with respect to beta partially, then del beta del eta will be minus I by 2. So again, when you will differentiate these expressions with respect to eta, and remember zeta xi eta and zeta eta xi are same. So again, zeta alpha will be function of alpha beta like this. Okay, so from here only two terms will come. You can compute it very easily, like zeta alpha alpha into half will come. Okay, del alpha del eta plus zeta alpha beta will come. Okay, from first term only. From first term only, zeta alpha beta will come. And then del beta, because you are differentiating partially with respect to eta, so del eta will come. It will be minus I by 2. Similarly, from the next term here, two terms will come. One will be xi alpha beta, okay, and del alpha del eta, which is half, plus when you will get zeta beta beta, then del eta again will come, minus I by 2. Okay. Now you will see that xi alpha beta its coefficient is minus I by 4, and this is also it should cancel out. So let me check out again, xi alpha beta and del alpha del eta. Del alpha del eta is half, so minus I by 2. So what will happen? Plus 1, all is same. So it is, it should be, okay, let me check again, because this xi alpha beta should cancel out. So, okay, xi alpha beta here. So del eta is minus I by 2. Okay, and minus I by 2 is coming from here. Xi beta del beta. I think it is missed. It should be plus. Del beta del xi is plus I by 2. So it should be plus I. So now you see this cancels out. Okay. And you will get 1 by 4 zeta alpha alpha plus zeta beta beta. So finally, therefore, PD1 becomes now del square zeta del square zeta del alpha square plus del square zeta del beta square. I am absorbing 1 by 4 factor in f. Let me put, because I absorb f, so f tilde, which is function of variables and first order derivatives only. So it is elliptic. So that completes the case 3 also. Hence PD1 will be elliptic, when s square minus 4RT less 0. And in this case, there is no characteristic directions. Okay. So this completes the discussions of canonical classification. Hope that you understand this. And in the next class, I will discuss wave equation. I will start wave equation. As I, on the first lecture clip, in the motivational introductions, I told you that I will be back and I will discuss 3 celebrated equations: wave equation, heat equation, and Laplace equation. So from next lecture, in the next lecture, I will start wave equation. So for now, goodbye.